In this module we continue to discuss electromagnetism and its applications and theories. Electric field is generated by a charge or charges in space. When a body B is placed near a body A, it experiences a force F. When both bodies are positive, they will have a repulsive interaction. If we move around this body B at any point around it, will experience a relative amount of force depending on how near or far body B is. This suggests that there is a field generated by body A that is generated around it. When we replace the charge body B and replace it by an arbitrary point that has a property of a unit charge Q0, we can write an expression for the charge as shown in the equation below. We can imagine this field E having the direction depending on the net charge of the mass. So if it is positive, then it is outward, and when it is negative, it is inward. We can also change the property of the point charge in terms of its direction. We can replace a test charge from a positive to a negative. Here we see the relationship between the electric field and force direction changes when the point charge direction is changed. It is clear that the electric field is just like the electric force in the sense that it is also a vector quantity. We can then expand equation 6 by incorporating the formulation of the electric force. We see this in equation 7, where the equation is reduced to Q here is the net charge of the body, R here is the distance between the source point and the test charge, and R hat is the direction of the electric field. If there are several source points or several charges with different magnitudes, the force experienced by the test charge, where for this case we have a negative test charge, is the sum of these source points. The equation that describes this net force is given by equation 8. The electric field experiencing the negative test charge is also the sum of these three source points, and it is given by equation 9. Electric fields are generated by a charged source point, and to understand them easily by visualization we create electric field lines. Electric field lines are imaginary lines or curves drawn in space which are pointed in the same direction as the electric field vector. So for a positive single charge, the electric field lines are drawn perpendicularly outward. For a negative single charge, the electric field lines are drawn inward. When two charges are brought closer together, their electric field lines interact with one another depending on the position and type of charge. For opposite charges where we know they will have an attraction with one another, their field lines connect from outward positive charge towards a negative charge as shown in the figure on the left. For same charges, where we know they will have a repulsive interaction with one another, their field lines do not intersect with one another as shown on the figure on the right. Sample problem. Consider 3-point charges located at the corners of a triangle as shown in the figure, where Q1 equals Q3 equals 5 microcoulomb, Q2 equals -2 microcoulomb, and A equals 0.1 meters. Find the electric field on Q3. Refer to the figure. At the location of Q3, the total electric field is a vector sum of the individual fields produced by Q1 and Q2. Note that the field exerted by Q1 on Q3 lies on the x and y plane, so we consider its components. So we write an expression of its component as a function of theta shown in equation A and B. So we write the sum of fields along x and y as in equation C and D. Let us consider solving the angle theta. By geometry we see that the sine and cosine of this angle can be expressed as these functions here. Consider the adjacent and hypotenuse parts. For the cosine function we have equation E and sine function as shown in equation F. We will substitute them later. Recall the expression of the electric field by two charges, we have equation 7. So we have for the field along X, which is the sum of the components from field 1 and field 2. We get that the sum of the field is a negative value that suggests that it favors going in the direction along the x-axis as indicated by equation G. Considering the field along the y-axis we have from equation D, we get that the net field along y is pointed upwards since it is positive as shown in equation H. Here we have the resultant field, which is expressed by its components along the x and y axis from equations G and H as shown by equation I. Based on the signs of its components, the resultant is oriented on the second quadrant as shown by the figure. We can also solve for the magnitude and direction of this resultant electric field. For the resultant we use the Pythagorean theorem as shown by equation J, which is about 1.5 meganewtons per coulomb. For the direction, we take the negative x-axis as the reference, and using the tangent function where we take its absolute value, we get that the resultant field is 8 degrees with respect to the negative x-axis. So far we have been using a familiar shape called the spherical, and we calculate its electric field using equation 7. Since objects that can hold a charge can be different, then its electric field equation must accommodate those shapes. Here we say that for irregularly shaped and even common shapes we use an integral function in order to measure the magnitude of their electric field. For thin wires we use the equation 10, where lambda here is the linear charge density of that wire. Similarly, for irregular sheet shape objects we use equation 11, where sigma here is the surface charge density. And lastly, for a volume-shaped object like a cylinder where the charge is all over its surface, we use equation 12, where ρ is the volume charge density. Sample problem. Electric charge Q is distributed uniformly around a thin ring of radius. Find the electric field at a point on the ring axis at a distance from the center of the ring. Here we divide the ring into infinitesimal segment ds as shown here. This small segment has a small charge we call as dq, and it exerts a field on a point P. Now if we have another segment that is identical to the previous one but positioned on the opposite side, we have a cancellation of the electric field along the y-axis. So we see that the net electric field is solely due to the x-axis. We write the net electric field as equation A. We consider now the integral function, which we write now as equation 7. We modify this function to incorporate the parameters of a charged ring as shown in equation B. Expanding further the integral, and we now left with the function with our distance as shown in equation C. The cosine function can be calculated by examining the figure as shown here in equation D. Substituting this back to the equation, we have function E. As we examine the problem, the distance r will not change as it exerts an electric field at point P, so that means the denominator is a constant, so we can factor it out as shown in equation F. We note that dq is a representative of the ring, so we consider the linear charge density function. The linear charge density is evaluated on the total length of the arc 0 to 2 pi a. So we can also factor out the linear charge density, and we arrive at the solution for the net electric field at point P as shown by the equation here. Sample problem. A positive electric charge Q is distributed uniformly along a line of length 2a lying along the axis between y equals -a and y equals a as shown in the figure. Find the electric field at point P on the x-axis at a distance x from the origin. Here we take a small segment dq of the rod and determine the electric field at point P by this segment. We see that the distance r is just the Pythagorean equation, and we notice that as we evaluate the charged rod the distance r changes. Examining the equation for r, we see that the distance x along the horizontal remains and only the y distance changes. Here we divide the rod into infinitesimal segment ds as shown here. This small segment has a small charge we call as dq, and it exerts a field on a point P. Now if we have another segment that is identical to the previous one but positioned on the opposite side, we have a cancellation of the electric field along the y-axis. So we see that the net electric field is solely due to the x-axis. We write the net electric field as A. We consider now the integral function, which we write now as equation 7. We modify this function to incorporate the parameters of a charged rod as shown in equation B. Expanding further the integral, and we now left with the function with r distance as shown in equation C. The cosine function can be calculated by examining the figure as shown here in equation D. Substituting this back to the equation, we have function A. We note that dq is a representative of the rod, so we consider the linear charge density function as shown by equation F. The linear charge density is evaluated on the total length of the arc 0 to 2 pi a. So equation E can be written as equation G. So we can also factor out the linear charge density, and we arrive at the solution for the net electric field at point P as shown by the equation here. We substitute the linear density as shown here, and finally we need to solve the integral factor in equation H. Note we retain the constant x, which we will use later in solving the integration. So we isolate the integral function of equation H. We let y as a function of tangent theta, and this in turn turns dy to a function of x times the squared secant theta. So we continue to manipulate the function further, and we arrive at a much simplified function of the integral as a function of secant as shown in equation I. So let us examine the solution of the integral or equation I and substitute back the parameters. Comparing the figure, we see that the sine function is given as a ratio of y over the length r. Substituting back the functions, we get a modified equation I. We then evaluate this integral from a to negative a, and we have the solution for the integral shown in equation J. We then substitute this back to the equation of the net electric field in equation H. Substituting back to equation H the solution of integral equation J, we arrive at the solution to the net electric field exerted by the charged rod onto a point P away from the rod shown by equation K. Sample problem. A disk of radius r has a uniform charge density sigma with units of coulomb meter squared. Find the electric potential at point P on the axis passing through the center of the disk. We can see from the figure. Some of the parameters are seen and calculated here, like the length d. We imagine that we take small circles with a charge of dq. Here we take a small segment dq of the disk and determine the electric field at point P by the segment. We see that the distance d is just the Pythagorean equation, and we notice that as we evaluate the charged disk the distance d changes or the r varies. Examining the equation for d, we see that the distance x along the horizontal remains and only the r distance changes. Here we divide the disk into infinitesimal segments of rings with dr as shown here. This small segment has a small charge we call as dq and it exerts a field on a point P. Now if we consider a point on the segment that is identical to the previous one but positioned on the opposite side, we have a cancellation of the electric field along the y-axis. So we see that the net electric field is solely due to the x-axis. We write the net electric field as equation A. We consider now the integral function which we write now as equation 7. We modify this function to incorporate the parameters of a charged disk as shown in equation B. Expanding further the integral, and we now left with the function with d distance as shown in equation C. The cosine function can be calculated by examining the figure as shown here in equation D. Substituting this back to the equation, we have function E. We note that dq is a representative of the disk, so we consider the surface charge density function as shown by equation F. The surface charge density is evaluated on the total radius of the disk 0 to r. We also substitute the value of the dq as a function of the surface density as shown by equation F. So equation E can be written as equation G. We also factor out the surface charge density and further simplify it with incorporation of the surface charge density as the total charge Q and the total area of the disk. We then have the function h where we need to solve the integral function. Considering the integral function and solving it, we also evaluate it from the total radius from 0 to r as shown in equation I. Finally, we have an expression for the integral function as shown in equation J. We then substitute back the solution for the integral back to our equation for the net electric field. So the electric field exerted on a point P is given by equation K. Electric dipole is a pair of point charges with equal magnitude but opposite signs in the presence of an electric field. The magnitude of the forces are the same but having an opposing direction such that the sum is given by equation 13. We see that the net force is equal to 0 along the x-axis. Considering net torque where the axis of rotation is positioned between these two charges, we recall the expression of torque is given by equation 14. Note that the direction of the torque is perpendicular to the plane. The net torque is given by equation 15 and we see that it is non-zero, thus the system will rotate in the presence of this electric field. Electric dipole moment is the product of the magnitude of the single charge and the distance between the charges, and it is given by the equation 16. Its direction is pointed towards the positive charge. We can then substitute this to the torque equation and we get equation 17. We see that the torque is maximum when the theta equals to 90 degrees shown here by equation 18, and its direction is also pointed towards the positive charge. Where we see that the dipole moment is given by equation 19, which is just the same. To measure the maximum torque, we see that by substituting the 90 degrees angle we get that it is equal to the dipole moment times the electric field E as shown in equation 20. Sample problem. An electric dipole in a uniform electric field of magnitude 5 times 10 to the power of 5 newtons per coulomb that is directed parallel to the plane of the figure. The charges are both 1.6 times 10 to the power of negative 19 coulomb with opposite signs. Both lie in the plane and are separated by 0.125 times 10 to the power of negative 9 meters. Determine, letter A, the net force exerted by the field on the dipole, letter B, the magnitude and direction of the electric dipole moment, and letter C, the magnitude and direction of the torque. For letter A. To determine the net force exerted by the field on the dipole, we sum the forces and we see that they are positioned along the x-axis, so there are no forces along y, so we cancel each other and result to 0. For letter B, to determine the magnitude and direction of the electric dipole moment, we recall the formula for dipole moment given in equation 18. We see that it is about 2 times 10 to the power of negative 29 coulomb meter. Its direction is pointed towards the positive charge. For letter C, the magnitude and direction of the torque, we recall equation 20 and we see that the magnitude is about 5.74 times 10 to the power of negative 24 Newton meters. For the direction we use the right-hand rule and we see that the torque is going out of page. That is it for now, and I hope you learned something new today. For questions and comments you may send them to diyeslearningstuff@gmail.com. You may review the slide on YouTube at @diyeslearningstuff. Note, please do not forget to use your school email. Also write your complete name and class section. Thank you for listening and see you next module.